Okay, so here is problem number 65 of chapter 22. We are given three scenarios, right? In part A, you have to find out um, a place where the electric field is in negative I directions. In part B, you have to do this when you have both I and J hats, both components present, and so is for the C, right? Now, you can generalize, this problem by assuming three sets of coordinates and go through rigorous calculations to find out where they are. You can also make your job a little easy by um, understanding these directions a little more. Okay, so for example, let's start with problem part A, where you want to find out where the electric field is going straight to the left, right? So that's basically what you want to find out. Now, if you have a point charge, since we know that all the electric fields are basically going away from it, right? You can quickly imagine or understand that any point which is somewhere here will only be able to apply of like show you an electric field like this if it is on the same, it is situated on the same line as this electric field is directed. So basically speaking, wherever this point is, this point should have the same y coordinate as your original point has, as your original 10 nanocoulomb charge has. So if this is 2 centimeter, this will also be 2 centimeters. So you don't have to actually solve for YA. It's given. That's like 2 centimeter. All you have to do is to find out XA, and or you can simply just find out R, because that's all you need, right? So your electric field is going to be, actually your electric field is just this distance, right? So your R is, in this case, this length. So I would just work with a general value of XA and then find out electric field at that point and then equate it with the value, the magnitude that's given to you, which is 225000. And if you find out magnitude of it and you equate it with 225000 and solve for X or XA, then you should be able to get where XA should be. For the second part, or for B basically, you have both positive X and positive Y. So let's say if your point is right here, actually it looks not exactly right. Maybe it's like this, X equals to 1, Y equals to 2, somewhere here. So you have now both your X and Y components are positive. In the part B, right, you have both I component and J components present, and then you have both of them to be positive. So you are looking at some place away from the origin, maybe here, we don't really know, but it has to be somewhere in this region, so that you have a vector like this, so that you have both X and Y components are positive. You can find out angle theta because you are given the electric field over there. You know that tangent or tan inverse Y over X gives you the theta. Once you know theta, you can also find out EX and EY using cosine and sine theta, and then find out what the XB or XB and YBs are, right? So you will have to solve for these guys, and using the EX and EY in terms of them to the values that are given to you, because EX is given as 161,000, EY is given as 80,500. So you can set up two equations, solve for XB and XA. XB and YB. And in the same ways, you will have solve C, right? So again, you are going to set up your 0.10 nanocoulomb charge over here, but now you have like a positive X and a negative Y. So you are trying to find out somewhere where your X component of the electric field is positive. So it's something like this. Your Y component is negative, and now you take it to be basically away from this charge, but in a different direction now. So you have a different angle to work with. You can similarly go through tan inverse y over x and find out ex and ey. Sorry, there's no division, it's just ex and ey, and then you can find out again xc, x, and yc for these two guys, and then again you can equate them to solve for xc and yc. Okay, so I'm going to stop here because I don't want to give you guys the whole solution, but you get the idea, right? So in each of these cases, you are going to basically look at the value that you're given. For the first case, you're given that the electric field is 225,000 with a negative I cap or I hat direction, which is basically this. Once you knew this and you knew that you didn't have to solve for YA, you could equate your electric field value calculated on the basis of this XA distance, and then you solve for XA. Similarly, for part B, what you did was you had both the X and Y components given to you. You could just simply take EY over EX and find out the angle with which and what direction you have your electric field going with respect to the positive X axis. So you could find out that theta. Once you know the theta, you can find out EX as E cosine theta and EY to be E sine theta, and these are given to you, right? These are given to be as 161,000 and 80,500. So now you have two equations and you have just two unknowns, xb and yb. So you solve from there. Moving on, you will do the same thing for part C, and you'll just have a new theta because your EY and EX are different. So you go on and find out again EX and EY in terms of cosine and sine, and then you solve for XC and YC. Okay, so I'm going to stop here and stop scrambling as well, but let me know if this is helpful. If not, I'll upload a new video. Thanks. Bye.